When we were last in class, we were having a discussion about using the inertial sensor to get the robot to self-level or self-balance. I thought we'd take a look at that now. So let's start off by having a look at what the inertial sensor can do. The inertial sensor is a combination of a 3-axis accelerometer and a 3-axis gyroscope. The accelerometer measures linear acceleration along each axis, and the gyroscope measures the rate of rotation about each axis. For the self-leveling robot, we're going to be using the gyroscopic outputs of the inertial sensor. So our 3 axes, the first one I'm going to talk about is the axis that runs straight through the robot from left to right, straight through the side of the robot. So we'll have a look at that running through around here. And when the robot tilts up or down, the rotation around this we call our pitch. The next axis we're going to look at is the one that runs straight through the robot from the back to the front. And when the robot rotates around this axis, it's actually tilting left and right, we call that our roll. And the last output that the gyroscope has is an axis that runs straight through the center of the robot, going from the bottom through to the top. And the rotation around this axis we call our yaw. Let's take a look at my example robot in RobotMesh Studio.
Okay, so let's have a look at how the robot performs or works here. So using the inertia sensor, when I take it to my ramp, first of all, some caveats here. I'm not a very good robot driver. Second thing, and this is helpful for the demonstration anyway, I have used Omni wheels on this robot. You can't tell, but I have. You'll notice that it starts sliding down the ramp when I get it sideways. So if you see it drifting a lot on the ramp, that's because of the Omni wheels that I'm using on the robot. Now, the first thing I did was I used the pitch. So I'm looking at the robot now and it's pitching up. So when it's pitching up, the robot wants to drive forward. So that's giving me a positive pitch and I'm translating that directly into positive forward motion in the drivetrain. So it's basically just a multiplication of the pitch value and put that into the drivetrain. As the pitch goes up over the top, it'll level out, become 0. The power to the drivetrain will also become 0. If it goes over the top, the pitch will actually start to go negative. The power to the drivetrain will go negative, and the robot will actually come back to the center position as well. So when I do that and I press my button to actually get it to perform that operation, I'll just press my button, it goes up to the top, and it basically stops at the top. If it was to go over the top, and press it again, it'll back because the negative pitch will actually make the motors run backwards. So I thought that was really good and I was quite happy when I first did that. And that's probably all you would really need for the tipping point game. However, because we're looking this not just on the tipping point, I thought we'd have a look at some other issues. One of the things was if I got the robot too far on the side like it is now, and I'm not a very good driver, so probably I do this all the time, when I hit the button to go up, yes, it will go up, but it's not going to turn, so it's going to kind of just drive off the edge, which is a bit of a pain for me. So, and sometimes I'll lose it off the edge altogether. So the next thing I came up with, I thought, well, I should make sure the robot straightens itself before it climbs the platform. So if I turn the robot sideways, you'll see that the left-hand side, the way it's sitting now, is actually tipping down. So I could actually now use the roll push value coming from the inertia sensor. And when I use the roll value, I can actually get it to straighten up so that there's no roll. So I'm basically doing exactly what I did with the pitch into the forward motion. Into the turning motion, I'm applying whatever value the roll is, with a little bit of maths, multiplying it by a factor, um, to basically give enough power to actually turn it. So when I actually add roll to it, now will run the one with the roll on it. It turns around and drives up the hill. So I thought that is fantastic. That works really well. Still had some problems with that because if I was too close to the edge, because I'm just, as soon as I instigate the command, it basically is doing the roll and the pitch at exactly the same time. What happens is, and I'll just back it back a little bit, what happens is that it does a wide turn because it's actually trying to go up and turn at the same time. So, and I went over the edge. So there's a possibility that it will get stuck on the edge if you do it that way. Uh, yep, okay. So if I was a little bit further away from the edge, I can kind of just make it, maybe not. So, and I think we'll call for a reset of the robot at that point in time. So the next thing I thought, well, what I should do is to counteract that problem would be to actually make sure the robot straightens up. So make sure the roll is almost completely eliminated within about a degree. I've set this out to. So I'll let it work on the roll first. Once the roll is within a degree of 0, then we can have the robot work on the actual pitch angle and straighten that out. So here we go. If I have it this way, now when I press my button, it will straighten up first and then drive up to the top. And that gives me a nice straight move up, and it doesn't try to do a big wide turn. So I will actually turn on the spot because I'm using the spin turn. You'll notice that. So even if I'm right down close to the edge, it's reasonably good. It will just straighten up first and load it up where it is. So that's where I want it to be. So that actually works quite well. There was a couple of other little things that you have to think about. One is if I go over, if I'm pitching down instead of up, like this, I've got to now, I don't want the robot to have to turn right around and then come back up like that, like that. What I really want it to do is actually, I'll do that again. What I really want it to do is to straighten up in the reverse way. So what I did was when I do this test now, what it actually does is it works out that it's going downhill first, and then it changes the direction of the roll correction so that it'll actually align backwards up the ramp. So I do that. So if I'm over that way, it will go backwards up the ramp. And if I go this way, it will straighten up and go forwards. And of course, if I take it beyond that halfway mark, it will reverse back up like that. So, and the last thing that I wanted to test, was, so I'm on the ramp now and I need to actually see, well, how does it go if I interfere with the robot? Now I can't tip the ramp and I haven't built the seesaw mechanism or anything like that. So I thought if I just add another robot, just as bad at driving this robot, into the mix so that I can give it a bit of a push to see how it reacts to if it gets pushed by another vehicle or some. So if I push it out of the way and it finds itself on the platform. So I'll do that again, a little bit harder this time. And straight away it gets it out. And I'm pushing as hard as I can. It's fighting me on that. Okay, so there you go. That's basically how I ended up with, I think, the results I'm getting, and I think that's quite a good way of actually doing it. So I'm straightening up first, and then I'm going straight up the hill. And of course, I'm still monitoring the roll. So if it did drift as it was going up the hill, it would automatically straighten itself as well. So let's have a look at how it works in the code now. So looking at the code, you might be surprised to see how small amount of code I've actually got here. Um, And let's just have a look. So there's not a lot for us to actually worry about and go through here because I've kept it as simple as possible. I did make this up with the latch button so that you click the button once and it would just keep it in automatic mode. If it saw some pitch, it'd automatically take over and start to go up the ramp. But I found that latching buttons is probably not good for competitions unless your driver's really good at remembering whether they're on or off on the button. You're probably better off having two buttons to set a switch on or off. And then again, I thought about this as a whole process. Well, the driver's not going to be doing anything else but just keeping it on the ramp. So why can't he just leave his finger on the button if he wants to do this? And so I have just made it up so at this point in time, he can just hold his finger on the right um, top bumper button, which is button R1, and we'll have a look at what I do here. I do set the braking type to hold. It's kind of, I'm not sure really matters. Okay. I think I experimented with that to try to see if I could stop it from rolling down the hill sideways, but of course that makes no difference to the Omni wheels. I set a deadband for 20, that's just my joystick. Probably the Vex joysticks are much better. So we just start a loop off here, and this is my um, basically auto leveling sequence here, these three lines. And here is just, if I'm not pressing the button, it's going to take the X and Y positions from the current joystick positions, which is just a normal joystick driving. And I'm using the drivetrain arcade mode to do this. And I'm basically just getting a X value, so my left and right value, my turning value, and my Y value, my forward and backwards value, and applying it to the arcade mechanism of the drivetrain. Um, and of course, I've set my drivetrain up with four motors that you can obviously see there. Now we can talk about drivetrains. Most of you guys know how to do the drivetrain, so it doesn't really matter. Let's have a look at what happens with the inertia sensor. The inertia sensor, and we talked about before, can measure roll, pitch. It can measure a lot of other things because we've already talked about that, but the roll and the pitch are what we're going to look at. So I'm starting off by looking at the X, which is basically going to be my turning. So I'm looking at the roll and I'm saying, okay, let's set the X value to what the value is that I'm getting from the roll value multiplied by, and to get it to turn the right way, -25. So I'm multiplying the factor by 25 because it comes up, you know, especially in my ramp that I've got here, it's getting readings of about, 6 degrees raising on the platform. So it will actually it'll easily get up to 100, but it's not really, and it doesn't matter. I can push the value over 100%. It'll just drive the robot at 100% if I put in anything over that 100%. So this is going to give me my turning factor here. And again, the negative is just so that it turns the right way, and that's set up so that it turns the right way going forward. After that, a little bit of tricky maths here, and it's not really tricky maths. I then needed to actually make a decision whether the robot was facing up or down because I really wanted it to turn so that the back was facing up to the ramp if the robot was facing down, and if the robot was facing up, I wanted to turn so the front was pointing to the top of the ramp. So to do that, I had to change which way the robot would turn if the robot was facing backwards. To do that, I actually find out whether the robot is facing up or down by actually taking the pitch reading now, and I'm finding out whether the pitch is in the negative or in the positive. If it's in the negative, it's facing down. If the pitch is positive, that means the nose is up on the robot and it's facing up. Now, I do a little bit of a trick here, and I know someone will probably say to me, you can import the maths module and you can use the sine function from the maths module, but for one line of code, if I'm not using the maths module for anything else, I don't think it's worth importing it. So instead of doing that, I do a quick calculation. I take the absolute value of the pitch. So if it's a negative number, it'll just give me the positive number of the same. So if say it's -5, it'll make it +5. And I divide it by the pitch value. So it's itself. So it's going to say, if it was -5, it's going to go 5 divided by -5, and that's going to be -1. If it was 5, the absolute value of 5 is still 5, so it's going to be 5 divided by 5, and it's going to be 1. So if it's positive, it's going to time my equation by 1. If my pitch is negative, that means it's going, the back is facing up. It's going to times my value by -1 and give me, change the sign. Okay, so basically that's all this little bit of code here that might look a little bit weird from the maths perspective, and hopefully now that I've explained it, it doesn't look so weird. The next line that I've got is I introduced this thing where it's testing whether the roll is pretty straight or not. And at the moment, I've got it straight to me is anything that is less than, anything that's kind of less than 2 degrees, or if you look at this, it's anything that is over 2 degrees, right? Anything that is greater than 2 degrees, it is actually going to not set a Y value, it's going to set the Y value to 0. So Y will be 0, it won't actually try to drive the robot up or down if the current roll position is anything greater than 2. Once the roll becomes less than 2 degrees or 2 degrees and less, it will actually do this else part of this statement, and that's basically take the pitch value and multiply it by 25. And like I said before, if the pitch value is facing up, it'll be positive, and it'll actually give me a positive number, which it'll apply to the power of the motors to go up. So basically, it will then set the Y value to the pitch value multiplied by 25 once this roll here becomes, well, when it's not greater than 2, so 2 and under. Now, and that's taking the absolute value from the roll. And again, this is so that I can say, well, if it's -2, that becomes 2. Well, I should say -3, because -3 is going to be greater than, -3 will turn into a +3, and that's going to be greater than 2. And that's why, again, I use the absolute value here when I take the reading for the roll. That's it. End of story. It's pumped it into those two, exactly the same as my joystick pumps it in. So if I'm holding my finger on the button, it will drive the arcade and actually level the robot with those 3 lines. And just to have a look at it again, if I go into my Mimic and I run it, wait for it to come alive and get it onto my ramp, move my mouse out of the way and press the button, straightens up, and there it is. I try to push it off with my joystick. I can't actually. And as soon as it goes off, you can press the button and hold it back on. So that's it. I think you guys should have a play with this. It's quite easy. The base bot that I gave you guys to start with, that you're building on at the moment, has the inertia sensor. Well, it's the same base that I'm using now. It has the inertia sensor there. It is configured as part of the drivetrain as well. So you could actually have a look at that code and give it a go and try it out. So I'll flip back to my code so you can get a good look at it. And I'll stop it from running. And there it is. So good luck and let us know how you go.